Welcome to Video 8 Part 2. So this is the second half of the Video 8 in the series, and this one what we're going to be doing is carrying on with the changes that I've got here and the updates to the design. So we're going to be doing the VGA card side of things here. So the first half really was very much sorting out the main Nanocomp CPU, RAM and ROM boards and simplifying the layout there. And then this half what we're going to be doing is removing a lot of the ribbon cables and tidying up the layout, and also consolidating about 4 of the logic chips into a single programmable logic device. Okay, so the data lines, we've got the data lines on this ribbon cable that goes over to the side of the dual port video RAM over here, which is kind of buried behind these cables here. So we're going to pull these out and pull those out of there as well. So we don't need those now. And so rather than wiring into the side over here, what we're going to do is to wire all of these up to here. So we're just going to need some white cables to go from there to there. We need to do that in a way that will also then allow us to wire in these signals. So these signals are going to go from here to here, and then the other side, there's about 5 signals on this side that are going to go to here to here. We just need to be mindful that when we're doing this, we probably need to make sure that these are actually leaving enough space for us to access these. So we probably need the lines to go over the top here and leave this space down here free. Okay, so I think what I'll also do is I'll unplug these for the moment as well, just because it just gives us a bit more space. So we're just going to unplug those. And we're going to unplug these ones as well. Now these other fly leads and things that we've got flying around at the moment are going to tidy those up in a bit, but I just wanted to do these bulk cables first of all to make things. May still end up with this cable here, just because to get all 8 lines here to go all the way across here will still be a little bit messy. So I'm not saying we'll get rid of it, all of them, but we can certainly get rid of a number of them that will make life a little bit neater and tidier. And you can see there's a lot of the control logic here has all got its hacked together gates and things around, and so we're going to tidy a lot of this up, and there'll be a PLD. This is going to get moved, and we're going to have this is going to move down, and then we're going to put the PLD in here, which is going to take up the logic gates from there, and also from there. So that's going to make things a lot cleaner, hopefully, by the time we finish this. Okay, so we're first of all going to be putting in the address bus lines between the 2 video RAM chips. So by putting the 2 address buses together like this, it means we don't need the ribbon cable coming across from the dual port RAM chip over on the right there over to the lower video RAM chip. When putting these sort of bus connections in, I like to try and bend them away from the chip so there's a bit more space for getting access for test probes and things like that. So we've done the data bus buffers now. We're just moving a few of the control signals around and out the way, and then we're going to put in the 5 higher address bus lines between the 2 chips here. Again, we're bending these away from the chips as we do them. We'll just tie those up together. And now we're going to be wiring up the lower address lines on the right hand side here. Again, trying to bend these away from the chip so that leaves a bit of space for putting in test probes and things. And we've just about done all those, and once we've done the address lines, we're going to be removing all the logic chips, a lot of the control lines, and tidying things up. So removing all the various logic chips, a lot of the control signals, and we're going to be moving the top address buffer down a bit to make space for the PLD. So just move that down. Going to move the address lines and then put new address lines in for the buffer to the CRTC address lines. So we're just putting those in. Then we will put the PLD in the above that buffer there and put a chip label on it. So this has been done at about 30 times speed, not 15, as I said earlier. So what we're going to be doing now is I've had to make a few changes to this PLD. So I needed a inverted Y0 and an uninverted Y0. So all these outputs here are normally inverted, so they're active low, and I needed an active high output here. So I've added or changed a pin on this PLD that I wasn't using to be Y0. And what we're just going to do now is to go through and program that PLD. There's also a few changes to the original video PLD. Now I think that was called video 2 for one reason or other. I called it version 2, I think, to start with. So I've called that VGA 2, the existing one, and then we're going to also be doing this one, VGA 1. And so what I'm just going to be doing is leading you through some of those configuration changes. We're going to program those PLDs, and then we'll start to wire up the changes, because there are a few wiring changes associated with these. Let's just look at the changes that we've made to the Nanocomp address decoder. So what I've got here on the right hand side, we've got the memory map decoder from the previous video. So that was video 7, and the V here refers to the version of the Nanocomp, so I'm trying to keep now the schematic and the configuration files for all of the PLDs with the same version number, so that I don't get quite so confused between the different versions of the different components. So you can see here within the file here, we've added a Y0 positive logic in place of Y6, and this is because I didn't want to have to include an extra inverter, and so I thought I could use a spare pin that we had here. So we had the Y6 pin over here that we weren't using for anything at the moment, and what I've done now is you now have a Y0 VRAM non-inverted pin. So most of the chip selects are active low, whereas this one is an active high. So if we then go through and look at the diagram here, so the pin out diagram, we now have Y0 active high as opposed to Y0 active low. And just to avoid conflicts on pins and things, I've changed the labels there, and we have a definition here, so that this definition here is inverted. This high one is just a normal value. So what we're going to do now is to compile this in WinCUPL. So if we just compile this, and it's just warning us that there are some of the signals on the D latches have not got any configuration. And then if we run up XG Pro, I've already taken out the address decoder. We've got our chip is correct, so let's just read the current value just to see. Yep. So now if we load, we want the Nanocomp JED file, which is the output from there. And if we now program that, there we go. Okay, so I'm just going to fit that back in the board. So just going to put this PLD back in. Make sure the ground and all the other signals are lined up. Yep. Okay. So you can see here the label I've also updated. So we've got a Y0 signal on there which isn't currently connected to anything. So then we're also going to take out the original VGA configuration. I'm just going to take that out and put that in the EPROM programmer, and we will have a look at it's in the EPROM programmer there. So if we now have a look at the changes that we're making for our video logic VGA2, the changes we've got here are we've removed the display enable inputs and outputs because we needed extra flip-flops for delaying the cursor by 2 dot clocks. So what we've done here is we're only taking the cursor in, and the display enable is no longer coming in. So you can see over here, no more display enable here. And then the display enable out signals are now cursor 1 and cursor 2. And the cursor 2 is delayed by 2 clock signals, and that will now be combined with the shift register dot output. And you can see down here, we will now have our 2 cursor pins, and then what we have here is the cursor input signal is mapped to the D input for cursor 1, and then cursor 1 output goes into cursor 2 D input, and then our foreground background determination has now got the shift register dot out combined XORed with cursor 2. So that's the cursor signal, which is now delayed by 2 dot clocks. So this should mean now that our cursor will line up with the rest of the characters. So that's all we've got on that one. So what we're going to do now is to go into WinCUPL, compile that one. So this is our Video Logic 2, which is our original one. And if we just turn off the project there and compile this, this will probably fail when we compile it, because it will may complain about the number of files we've got overwriting an existing one. Oh, it didn't. That's good. Okay, so that has compiled that okay. So now we have the Video Logic 2 chip already in the XG Pro, so I'm just going to read that to make sure it's all okay. Yep. So now we're going to load in our VGA 2. So this was our original VGA PLD. And now I'm going to program that. There we go. So that's all programmed as well. Just put this ground, set that signal, that's VCC, yep. And then finally, this is our new PLD. This is going to be used, this is our VGA1, as we're going to call it. So I'm just going to put a chip label on there. We just switch back to screen share. I created some more chip label layouts, so I've modified the chip label layout. So you can see here we had the Y0, and now we've got the non-inverted Y0 for the address decoder. Some changes around the cursor, removing display enable, and you can see on this one now, this is our new one, and I'll go into a bit more detail about this, but you can see we've got display enable in, we've got some display enable out, and various enable signals as well for all the other chips, and the input is A0, our video read write, inverted Y0 and Y0. So if we go to, this is the new VGA logic that we've done. Now what this is doing is replacing a number of the logic gates that we had on our diagram here. So these logic gates that were taking a variety of input, the video RAM read write, the Y0 inverted Y0, A0 inverted A0, and we're producing the buffer, bidirectional buffer enable signals, the read write signals for the individual video RAM chips, and also the output enable signals for those chips as well. So what this is going to do now, we have the A0 signal, the 25 megahertz dot clock, we have our video read write signal, which is our shortened read write signal, where we're using the Q signal from the CPU to shorten the read write signal to about 250 nanoseconds. The main read write signal from the CPU, and that has a period of about 1 microsecond or 1000 nanoseconds. We've also got inverted Y and the non-inverted Y inputs, display enable, and now the display enable is going to be delayed by 4 clock cycles, which was one of the timings we found in the previous video where the characters were shifted over a little. So previously I think we had 2 dot clock cycles, and now I think we need another 2 dot clock cycles. So what this is going to result in is 4 flip-flops delay for our display enable signal. And then we have our character read write output. We have our character output enable. We have our character buffer chip enable, and then we have the color output enable, the color read write, the color buffer, and then our display enable output. And then we just got the definitions, the input pins, definitions, the output pins, and then these are really our mapping. So you can see that our display enable goes into the first D latch input, the output of the first D latch goes into the second one, the second one goes into the third one, and then the third one is coming out here. Then we've got our signals for the character RAM read write control, which is taking the inverted video read write signal and the A0, and then the color one is similar but uses the inverted A0 signal. So this means the character is because of the logic here, the character read write will be enabled when A0 is 1, and the color will be enabled when A0 is 0. But the way how these logic gates work out was in the spreadsheet that we'd had previously, and the logic gates we've just seen. And similarly, we've got the Y0 and A0 signals are combined in these ways to control the buffer chip enable, so that we only enable the bidirectional buffer when the CPU is accessing the video RAM, and the characters enabled when A0 is 1 and the color is enabled when A0 is 0, the way how this logic works. And then finally we've got the output enable for the RAM, where we're having to disable the output from this a little bit before we get the buffer signals coming in from the CPU. I was finding that there were sometimes timing issues of this that was actually causing the video RAM to get odd results from time to time. So these are the symbols that we need here. This should actually remove 3 or 4 of the logic chips that we had previously. So I'm just going to go into WinCPO and load up Video Logic 1. Video Logic 1. We'll just close the project, and we will just get rid of Video Logic 2 because we don't need that for the moment. Just compile that. It will probably crash because of that message. No, it didn't. Okay, that's good. And so that should mean we now have a JD1 file. Got the chip in the programmer, so I'm going to go into XG Pro. We'll just read the configuration first just to verify it's talking to it okay. Okay. Now we're going to load our VGA1, which is our new one. And now we're just going to program that. There we go. So I'll just remove that and plug it back into the board. There we go. So remove that, and as the ground signal is up at this corner, and we haven't wired in the VCC yet, so that just fits in there nicely. And what I've tried to do is to make sure that the various signals and things should make it easier to route from the board there. So now what we're going to need to do is to make 1 or 2 changes to this PLD. So there's a Y0 here that needs to go into here. There's the display enable is no longer being handled over here, so display enable is going to have to come down here and then come out over to our buffer over here. And then I'm also going to wire in all of the address signals from here. So rather than relying on this cable here for wiring all the address signals down to here, what I'm going to do is to wire in some green lines from here down to the buffer chips down the bottom here as well. So we're just going to be taking these signals out here. So we'll just take these out here. Take those signals out there. And then we're going to be wiring in these signals down here. Now the only thing we need to be aware of is obviously that A0 doesn't go to this one initially, because A0 is obviously used for our signals for the over here, so it's going to start at A1, so we just need to make sure we wire these up correctly. And if we have a look at the diagram here, we can see that in fact the first pin down here is A1, A2, A3 goes up to A8. Now I should say here that I've relabeled the chip labels for these chips have been relabeled, but these 541s on the schematic have still got the original going from 7 down to 0. I've relabeled these on the chip labels from 0 to 7, so it makes it a little bit easier, although obviously in this particular case it really should be A1 to 8 to make it even less chance of making mistakes. But we're just going to wire these up now. So I've recorded this at 30 times real speed, so we're just hooking in the address lines down to the buffers down there, and now we're just going to plug in the various control signals. We're plugging in the Y0 and inverted Y0 enable signals and the clock, and then we're going to hook in the display enable signal and the various other control signals, read write A0. Now we need to put in the chip enable, output enable and the buffer enable signals as well, and then we're going to put in the character latch enable on the left hand side here. Then we're going to hook up the various row address columns and the output from the character latch and all the CRTC addresses. So finished plugging everything in. All of the cables have either been removed or we've tidied them up a lot, so we still have the ribbon cable for the video address signals coming from CRTC over here, and the row address lines we've shortened the cable a little so it's not quite as messy. We've wired up the extra lines to the PLD for the address decoder. We've wired in the clocks. We've wired in the various additional signals going to our new PLD here. That PLD is now hooked into all the various chip enable, read write and output enable signals down here. We've plugged everything in, so it should be working. So what I'm going to do now is to switch over to the video capture device. So that'll be blank, and we will connect the power and switch it on. The only interesting thing is it looks like it's working reasonably well, except for it looks like some of the bits may have been so it looks like we've got some bits missing here, so there may be an issue with one of the address lines somewhere. So I'm just going to turn it off and to check that out, but other than that it all seems to be working pretty well. And we can also see that the cursor is almost completely underneath the first letter there, and when we run our test pattern we should be able to see whether or not we've got everything going all the way up to the edges as well. So it looks like most of the things we've done are correct. The only issue we've got here is some of the address lines are probably reversed. Very simple check, and in fact it was as I suspected. When I was plugging in these cables I've reversed the color sequence. So if you see here it goes purple, blue, green, yellow, but plugged in here I've actually got the yellow and green reversed. So if we just swap those around, then we should correct our problem. Right, that's that. So let's switch back to the VGA capture card, and in fact now it's now looking like we expect it to be. So what I'm just going to do now is to run up the test program, just to put a test pattern on here so we can see how things are looking. So I've just loaded my CRT5 test program that I used in earlier videos. I'm just going to run this, and we'd expect this to give us a test pattern. We seem to have everything at the top. We can see that the cursor seems to be flashing underneath there. So you'll notice that with this test pattern that the end of the line we're just missing a little bit of the characters there, and there might possibly be an extra little bit at the beginning. It's difficult to tell on the video capture device, but I'll check this on the standard monitor in a little bit. But what I noticed as I was reviewing some of the video before I published it was that in the definitions for the display enable, you can see here that the display enable in goes into DE1, then DE1D is the D-latch flip-flop delay, then DE1 goes into DE2D, and then DE2 goes into DE3D, so that's 3 delays. But when we're actually taking the output from DE3, we're not putting it into the D latch there, so we need to put the .D in there, and I think that should give us our extra clock delay. So this is our Video Logic 1 PLD. What I'm going to do is to go into WinCUPL. I'm going to open that. Going to compile it. There we go, compilation successful. We did actually get an error and it crashed them this time. And then we're going to go into XG Pro. I just need to turn off the NanoComp. We're going to take the chip out, put it in the EPROM programmer. So we'll just read it to make sure it's in okay. Yep. And now we're going to load our VGA 1GED file and program it. So that's completed. So I'm just going to unplug that and put it back into the board. And then we'll rerun this and see whether or not this has made any difference. So power that on. Let's go to the VGA capture screen, and I will just download the test program again. It might have made a little bit better, but it's there's still perhaps about 1 pixel still. So what I'm going to do now is to have a look at that on the monitor, and then we'll come back. So I've hooked up the document camera looking at a physical VGA monitor, and when I hit the auto adjust on the VGA monitor, it's now looking pretty good. So I think it's just an artifact of the VGA capture card is probably about a pixel or 2 out, but it looks okay here. So that looks good enough for me. So we now have resolved the timing issues with the flip-flop delays that we've introduced to the cursor and the display enable. Now the only issue we really have left now is when we execute the update to the monitor, we can see that there is a little bit of flicker artifacts on the display as it updates. So the only thing we really need left to do now is to see, can we resolve that flicker? Now the obvious way is, what you can do is to look at the vertical sync signal and display enable signal and only update the display when display enable is blanking out the video. So in this way, if we only updated the display during the video blanking period, then we wouldn't see that. So I think what I'm going to do is to hook up a signal so that the PIA can see what the display enable and the horizontal and vertical sync signals are doing, and then we can choose to only update the display during the blanking period. So this is a comparison of a modified code which is actually waiting for the display enable signal. So let me just show you what the original code does. So this is clearing the screen and then displaying our test pattern. 4, 3, 2, 1. So it comes in a fraction of a second. So I'm just going to do now is to load the modified version of this, and what I've done here is I'm checking to see if the display enable signal is high for a couple of clock cycles before I actually do any updating of the screen. So this slows it down a fair bit, but it does actually prevent the screen from showing snow and artifacts. 5, 4, 3, 2, 1, go.
So you can see it's a fair bit slower, and so this has actually stopped the snow effect, but it's probably a little bit excessive in what we're doing. So one of the things I'll think about is if there's ways how I can change the timing signals so that both the CPU and the CRTC can access the memory together and to cooperate. On some early models of PC, the CPU clock and the video clock were synchronized so that the CPU and the CRTC would look at the memory on alternate clock cycles, but the trouble is the CPU here can only run at about 1 megahertz of the clock cycle, and the CRTC character clock is running at about 3 megahertz, so it makes it much more difficult. But I'll have a look at some of the timing signals and see whether or not we might be able to do something clever with the PLD logic. I'm just going to show you how I modified the test program. So CRT5 was the previous test program I'm using, and these are the changes for CRT6. So the main things I've done here is I've included the port B, control port B, and what I've actually done is wired in the display enable signal that comes out of the PLD to the PIA port B pin 7. And you'll see when we go down here what that means. Now you can see here that the VRAM top originally had set at the very top of video RAM, but really it's been unnecessary to clear the entire 8K of video RAM or 16K of video RAM even, and so I've just changed this to do the lower amount. And then we've also got here at the beginning where we're clearing the accumulator and initializing the parallel port or the PIA port. So all we're doing here is setting the top 4 bits for input on port B and making sure the port control register is set for accessing the data. Then before we do each operation interacting with a screen, so in the clear screen what I'm doing is waiting for a vertical sync display enable. So what that vertical sync display enable we'll have a look at in a minute, but what I found is when I was doing this and waiting for the vertical sync display enable for every character, it was taking a very long time. So what I've done here is only doing this once a line. So what I'm doing here is setting Y to be 8080. We decrement Y each time, and so we only do this wait for the vertical sync display enable once per line. So just speeded things up a little bit. Then most of the rest of the things are only doing this wait for vertical sync display enable occasionally, and you can see in the print digit before we actually update the digit we're doing that. Similarly for the print hex we're doing this check, and then the actual check itself, what we do is we're loading A with a mask. So this is the highest bit on port B. We do a bit test on port B. So if display enable is preventing the display from being updated, it will be a 1 in this particular case. And then what we do is we check to see if it's still a 1. If it's a 0, then we just go back, because chances are that we've actually got quite a short period of the horizontal sync. And if we have a look at the timing, I've got the vertical sync, horizontal sync, and the display enable. And we can see here that display enable is actually high and disabling the output for quite a bit longer than the vertical sync signal here. And in fact, it takes into account the lines at the beginning and the end of the display as well. We don't really want to base this on the vertical sync because the vertical sync period here is 508 microseconds, and if we look at the period here of the blank horizontal lines and the vertical refresh frequency, that's 1.6 milliseconds, so that's almost 3 times longer. If we look at the horizontal refresh interval, then these are only about 6 microseconds, so that's about 6 CPU clock cycles. And given that most CPU instructions take at least 2 clock cycles, when we look to see how many instruction clock cycles the test we're doing, then if the value is high sometime at this point in time, by the time we do the second test it will probably be low, unless we're in this long period here So the reason why we're doing 2-bit tests on it is to say, are we in the sync period here? Now, what I should really do is to put some sort of cache in here so I don't have to keep on polling the period here. We should really be able to use timers and things like that, ideally, to be able to tell whether or not we still need to keep checking it. But for the moment, it's a little inefficient, but at the end of the day, it stops the interference on the screen. So that's the end of part 2 of video 8, where we've been tidying up the NanoComp and the video controller card. So we've completed all these steps down the bottom here, and we've also now worked out a way of preventing the display interference during video RAM updates. It's a little inefficient, but we can look at better ways of doing this in future videos. So in the next video, what I'll be looking at is implementing a simple Tetris clone using the custom characters in the display character generator. If you don't want to miss out on future videos, please hit subscribe. And if you found it interesting, please click like. Thanks for watching.